Miss Asmus here with our 3.4 notes video. We're going to be continuing our periodic trends with a part 2. We're going to be learning about 2 more periodic trends, and these are actually impacted by 2 of the things we learned about in our trends video last week. So these trends are going to be ionization energy and electronegativity. But before we learn what these are, we're going to do a quick review of the last few and how those might impact these trends. So here, just a reminder of the groups, which are the columns on the periodic table, and the important trend to know about these is that those shielding electrons are going to increase in number as you go down the group. So as you go down a group, there are more energy levels, so there are more electrons in between that nucleus with the positive charge and those valence electrons in that outermost energy level. So as you go down a group, there's going to be more energy levels, more shielding electrons, which means those valence electrons are going to be less attracted to the nucleus. They won't experience as much of that attraction. Then, as you go across the periods, or the rows on the periodic table, the most important trend to know here is that effective nuclear charge, which we call Z effective, ZF. And this is just how strong that nucleus actually feels to the valence electrons. So how much of that charge do those valence electrons actually experience? And so we calculate this by taking the number of protons in that nucleus and subtracting that number of shielding electrons that are in between the nucleus and those valence electrons in the highest energy level. So as you move across a period to the right, there are going to be more protons in that nucleus. And valence electrons are added too, but no additional shielding electrons are added. This means that those valence electrons are going to be able to experience more of the charge of the nucleus as there are more protons. Those protons will have a larger attractive force on those valence electrons as more protons are added. So that nucleus will have a stronger pull on the valence electrons. As you go across those periods to the right, that effective nuclear charge increases. So as you go across to the right, that nucleus will have a stronger pull on the electrons. The first of these trends here is ionization energy. So this deals with creating ions from these atoms and the energy that it takes to do that. So ionization energy is defined as the energy required to remove an electron from an atom or ion. So how much energy it will take to take that electron away from the atom that it is in. So as we know, the nucleus attracts electrons, and so if a nucleus has a really strong pull on electrons, that means the ionization is going to be very high. When there is a greater force of attraction between those electrons in the nucleus, it'll take a lot more energy to steal those electrons from that nucleus with a strong pull. Like here in this photo, the stronger you hold onto something, the more energy it's going to take to pull it away. So here we have some dogs fighting over a ball. You can think of the nucleus as just grabbing onto these electrons. The more charge it has, the less shielding there is, the more strongly they'll be held in, and so the harder it will be to take one of those electrons away. So now it's time to make a prediction on what this trend will be for ionization energy. So the 2 things I want you to be considering as you make this prediction are the effective nuclear charge. How would that impact the strength of the pull of the nucleus, as well as shielding? How is shielding going to impact the force of the nucleus that these valence electrons will feel? So take a minute and make a prediction about which nucleus will have the strongest pull on valence electrons. And then also make a prediction on the element that has the nucleus with the weakest pull on those valence electrons. Pause, make a prediction, and then we'll come back and discuss. Alright, hopefully you were able to pause and make a prediction. I'm going to remind you of how these trends follow. So this effective nuclear charge is going to increase across the periodic table. So as you go over to the right, this is going to be the greater charge, and so the greater force of attraction is going to be on the right of the periodic table. Then also with shielding, we know that the shielding is going to increase down the periodic table. All right, that we have more shielding electrons, and so that force is going to decrease as it goes down the periodic table. So the atoms on the bottom of the periodic table, those are going to have the weakest pull on valence electrons. If we put these two together, we know that at the top and at the right, there is going to be the strongest force of attraction, and so that is going to be fluorine that will have the strongest pull on valence electrons. And then, since we know that the bottom and the left is going to have the weakest pull on valence electrons, francium is going to be the one to lose electrons the easiest. It's going to have the weakest pull on those valence electrons. So we know when that nucleus has the strongest pull on electrons, that also means it's going to have the highest ionization energy. It's going to be the hardest to steal electrons from atoms that have that really strong pull on the valence electrons by that nucleus. So fluorine will have the highest ionization energy. It'll be really hard to steal any of fluorine's electrons. And then francium will have the lowest ionization energy because francium has a lot of shielding, and so those outer electrons do not experience a lot of attraction to the nucleus. They'll be the easiest to steal. And then the noble gases don't usually participate in reactions. They are very inert, and so we don't include them as we go through this ionization energy. So just recapping that reason behind ionization energy trends, the elements like fluorine are going to have a really high effective nuclear charge, and their valence electrons are relatively close to the nucleus. So they are close to the nucleus, don't have many shielding electrons there, and they have a high effective nuclear charge. And so that means there's going to be a strong pull, a strong attraction from the nucleus on those valence electrons in fluorine. And so it's going to take a lot of energy to pull an electron away. So that's why fluorine is going to have the highest ionization energy, and that trend increases as you go to the top right of the periodic table. The opposite is true with elements like francium, because they are going to have a lot of energy levels. There's going to be many shielding electrons in between that nucleus and those valence electrons, and so that nucleus is going to have a much weaker pull on the valence electrons. They're going to be easier to steal, so francium will have the lowest ionization energy at the bottom left. On to our next periodic trend, electronegativity. This is somewhat related to ionization energy as it deals with the strength of the pull of those nuclei. Electronegativity is going to be an atom's ability to attract electrons when bonded to another atom. So this happens in compounds when there are bonds between atoms. This affects how electrons are shared within molecules. And so it's going to follow the same trend as ionization energy, since both are related to that nucleus's pull and that force of attraction from the nucleus on electrons. So many atoms, when they bond with each other, they share electrons, but the sharing can be uneven based on which nucleus has a stronger pull on those electrons. So different atoms are going to have different electronegativity values, and that's simply going to be based on how strong that nucleus is at attracting electrons. This is going to lead to atoms sharing electrons unequally when they are bonded together. So take hydrogen, it's going to have less strong of a pull. Its nucleus only has one proton, and so it won't have a very strong pull, but fluorine is going to have that really high effective nuclear charge and not a lot of shielding. So it has that really strong pull on electrons. So when these two atoms are bonded together, fluorine's going to take most of those electrons closer to its nucleus simply because that attraction is stronger. So they will unequally share those electrons. And so as you can see in the bottom photo here, this is a density cloud about where those electrons might be occupying. And so most of the time there's a higher probability that they'll be closer to fluorine's nucleus since it has that stronger pull than hydrogen. So it's going to be less dense with electrons on the side of hydrogen and much more dense with electrons on the side of fluorine. And so because there are more electrons, that means that fluorine's side is going to have a more negative charge, while hydrogen's side is going to have a more positive charge. So we use this plus arrow to show this, that the positive end of this compound is going to be hydrogen, since there are fewer electrons, in fluorine, since there are more electrons there, is going to be the more negative end. Here is an electronegativity chart showing each element's ability to take those electrons closer to itself when it is bonded to another atom. And so the higher this electronegativity, this number, that means the stronger of that pull it's going to be, the more it will steal electrons. So here we see fluorine is really high, just like we saw before, because it has a really strong nucleus. And then francium is going to be the lowest electronegativity because it has a lower strength of attraction on those electrons. It's not going to be pulling electrons closer to itself since it is weaker. That force of attraction experienced from the nucleus is going to be weaker. So now discuss the electronegativity. What characteristics, properties, traits of an atom are going to impact that ability to draw electrons closer to itself? So why do some atoms pull more strongly on electrons than others? Pause the video, take a moment, write down some of the things you know. Hopefully you were able to pause the video. So let's go over some of these. Well, we know this is all based on the strength of that nucleus, the strength of that force of attraction. And so it's going to deal with that effective nuclear charge. The greater that effective nuclear charge, the more it would pull electrons towards itself. And it also has to do with shielding, as we know. The more shielded the nucleus is, the less force of attraction will be experienced by those valence electrons, the less that nucleus can attract other valence electrons towards it. So if it has a high effective nuclear charge and low amount of shielding, it's going to have a higher electronegativity. And on the other hand, with shielding, if it has lots of shielding and a low effective nuclear charge, that means it's not going to be able to pull those electrons as much. And so it will have a lower electronegativity. And so based on these, it's going to be pretty much the same as the ionization energy. The ones in the top right are going to have the highest electronegativity. The elements in the bottom left are going to have the lowest electronegativity. So here is a summary of the periodic trends we have learned. So in our last sense video, we learned about the atomic radius. That is going to be the largest down at the bottom left of the periodic table. Those are going to be the atoms with the largest radius. But then ionization energy and electronegativity we learned today, those are going to increase across the periodic table and increase as you go up the groups. They're going to decrease when you go down the groups. And so the strongest ionization energy and electronegativity is going to be at the top right with fluorine. And francium is going to be at the bottom left, and that's where the lowest electronegativity and ionization energy is. And both of these are simply based on how strongly that nucleus can attract electrons. Hopefully it was helpful to go through these periodic trends. Now you know what ionization energy and electronegativity are, and that they are based on that strength of the nucleus to attract electrons towards itself. And those are impacted by the effective nuclear charge and the shielding effect of electrons. Thanks for watching.